Okay, we have now reached the point where we're actually going to construct an experimental apparatus to measure the heat capacity ratio of a gas. So in 1812, the French Academy of Sciences announced a prize of 3,000 francs for the best method of determining the specific heat of gases. Now remember, people had been measuring the heat capacity of gases for some time. You just took a gas in a container, added a known amount of heat, measured the increase in pressure, or measured the increase in volume. However, these measurements were somewhat crude and very imprecise, and so the French Academy was looking for a better way to do this. So the question is, why is it that the French Academy were interested in this problem? So one thing that we do know is that they desired a more direct and quantitative confirmation of Laplace's suggestion that the speed of sound in air can be measured if we understood the adiabatic compressibility of the air. And we needed a better experimental apparatus to get that measurement. An interesting thing is that in a report about the prize written in 1813, it would appear that the prize had nothing to do with the speed of sound problem, but the real reason that this prize was being offered was it was thought that there was a link between specific heat and the heat of a chemical reaction. And you do remember that the formulas for determining the heat of a chemical reaction don't necessarily include a term for heat capacity. Now, if we want to measure how much a beaker of water will get warmer or get cooler by when we run a chemical reaction in it, we obviously have to think about the specific heat of the water. And chemical engineers certainly think about the specific heat of a reaction vessel because they want to make sure the reaction vessel can withstand the temperature changes that a chemical reaction will undergo. But the idea of the heat of a chemical reaction really does not involve the specific heat of the heat capacity does not involve the heat capacity of the container or the heat capacity of the materials going into the reaction. Now, other historians believe that the Academy was interested in this problem because it would help them understand the weather. At this moment in history, we had an agricultural revolution. The output of the agricultural sector was increasing dramatically. We could feed more and more people. Farming was put on a more scientific basis. And one of the things that we needed to do if we were going to keep increasing agricultural productivity was to be able to understand the weather. And we couldn't understand the weather without understanding the heat capacity of air. So you're free to decide which of these reasons the French Academy had when they offered the 3,000 franc prize, but that doesn't change the fact that in 1813, the winner was Delaroche and Berard, who won the prize by constructing a calorimeter at which a gas at a constant pressure was heated and allowed to cool. And in their publication, they did allude to Laplace's ideas about the speed of sound. Now, wait a minute, what does this have to do with the adiabatic expansion of gases and we're doing in the P-Chem experiment? Well, the second prize winners were Clement and Desormes, who were the ones who figured out that you can measure the heat capacity ratio of a gas by compressing the gas, releasing the pressure, putting the cap back on the bottle or the container, and then observing what happened next. So the experiment that we still do today actually was the second prize winner in the Academy of Science competition. Let's go back to our speed of sound problem. So now using this data from de la Roche's and Berard's calorimeter in 1816, Laplace was able to correct Newton's estimate for the speed of sound using their ratio of heat capacity at constant volume, heat capacity at constant pressure. And Laplace got a value of 345.35 meters per second. Note, I'm using the metric system now because this is after the French Revolution. But this compared very well to a measured value of 337.18 meters per second. This result was 10% off because they ignored the pressure effects on specific heat. So in other words, depending on the exact pressure that we're working at, the specific heat might change. But the error that they made gave Laplace the correct value, and you would think that everyone would be happy. So Clement and Desormes did not publish their results until 1818, 6 years after the prize was announced, and about 5 years after they won second prize for the adiabatic expansion of gases experiment that we still do today. All right, so let's wrap things up between the 1822 and 1828. So in 1822, Gay-Lussac and Welter measured this ratio using the adiabatic expansion method. So in 1823, Laplace now takes this more accurate data and starting with this ratio and correcting for water vapor, he got a value of 337.715 meters per second against a measured value of 340.889 meters per second. So we've got a very, very close theoretical measurement or theoretical calculation for the speed of sound in air. And just to place this into the larger context of history, in 1824, Sadi Carnot published reflections on the motive power of steam. All right, back to the speed of sound. So in 1825, Laplace suggested that the Bureau of Longitude measure the speed of sound. And this new value, combined with the data from Clement and Desormes, Gay-Lussac and Welter, produced a much better theoretical value for the speed of sound in air. So essentially, the speed of sound in air problem was solved in 1825, over 100 years after Newton had made his initial error, clapping his hands in front of a brick wall. And then finally, in 1828, using acoustic measurements, Dulong begins to measure the relative speeds of sound for a number of gases. Which brings us to our final slide, where I wish you a happy P-Chem. Enjoy your adiabatic expansion of gases experiment. Please remember to comment and like and give me the thumbs up. And if you want to know about the Carnot cycle, I have 2 series of videos about that. My next video will be on the discovery of the first law of thermodynamics. Thank you for watching and good luck.